All right. I think we'll just go ahead and get started. This is sort of going to be a continuation of Jax's talk from last week on an introduction to binary exploitation, except today we're going to be talking about Linux Heap exploitation, could be a GLIBC implementation. So we're going to be abusing malloc and free functionalities to achieve code execution, and there's a bunch of different ways you can do this. This talk's going to be broken up into a few parts. We're going to shortly go over how the heap works, some techniques. It's a very wide range of things, so it can kind of be hard to cover in one talk, but we're going to try our best with the most important free lists and malloc implementations. So we're going to start with the heap. We'll be using the workshop demo binary to sort of visualize what theory we learned by actually inspecting how the binary allocates stuff in real time. So we're going to go over the heap first, specifically that relating to GLIBC. GLIBC is derived from the PT malloc implementation. There are many implementations of allocators. PT malloc is derived from something called pthreads malloc, and it basically allows us to have heap arenas that are thread safe. We don't have to lock them, and we don't have to deal with multiple processes interacting with one heap. Each can have their own. We're going to talk a bit more about threaded heaps later as well. If you're unsure of what the heap is, it's basically, it will allow you to dynamically allocate space and memory to store something at runtime. Like the stack, it's going to be at a random address, or the base address is going to be random. And yeah. So like an example would be like if you need to have a browser open, you don't know how many tabs you're going to have open or when they're going to close, you use the heap for that. Malloc is going to be the function that allocates a heap chunk to us. It returns a pointer to that heap chunk. We see here the only argument it takes is the size of the heap chunk. And chunks will be aligned to a certain valid heap size. We'll talk about that later. We have free, which basically frees a chunk that was previously malloc. Free doesn't delete the chunk. It just tells the allocator, hey, this chunk here can be used for future allocations if it's serviceable. So we see the argument that takes is a pointer to a chunk to free. And I talked about this differently, or briefly. Different threads have different heaps and their own arenas. We're mostly going to be dealing with the main arena today. We'll cover what arenas are, but they basically store heap metadata that are used by malloc and free to service requests. So a very important example would be the heads of free lists, because malloc doesn't keep track of the linked list anywhere specific in memory. We'll just keep track of the head, and we're going to figure out how we can abuse that later. And other important metadata like global max fast, which is used to tell the heap what the maximum serviceable request size is, and etc. Or that's actually sysmap. That's a different variable. The main arena is located in the libc section. So sometimes the main arena's metadata can be stored inline in the heap, which can be very useful if we can leak the heap, because we're also getting a libc leak. So, and we can see a little visual on the right here from Azeria Labs. Chunk anatomy. So when you call malloc with a specific size, it's going to return a pointer to the chunk it allocated on the heap. So chunks are sized to the nearest 8-byte aligned serviceable size. So that means if I request a size of like 8, it's going to be serviced to 0x20 because that's the smallest heap size you can have, right? So heap chunks have metadata in them that are used by malloc and free when servicing future requests. We're going to see some of this metadata when we look at a free chunk. But right now, we can see we have, and all chunks will be somewhat like this, or exactly like this. We're going to have an empty quad word. This will be used as a prep size field if this chunk ever gets freed. Next, on the second quad word, we're going to have a size for the first 4 bytes. And then the last 3 nibbles is going to be a chunk, or these flags. A is the chunk that's not in the main heap and was allocated, so this chunk was basically serviced with mmap, and it's not going through all the standard checks usually. M chunk was mmapped and will be treated directly. and P, which is a very important flag, is the previous chunk is not free. That can be pretty cool if you're able to overwrite that with an opposite value. You can trick the heap into thinking a chunk that's in use is free. And then the user data, that's going to be what malloc returns. That's what we're going to be able to write to. So this is just the anatomy of a heap chunk. If we were to call malloc, fill it with user data, and then free this chunk, it's going to look something like this. So this chunk will be allocated, or not allocated, but linked into a free list or a free bin. There are different free lists it can be put into depending on if certain conditions are met, like the T-cache, the fast bins, the unsorted bins. From the unsorted bins, it might go to the small bins or the large bins. And in certain situations, it might not even get linked into a list, and it might just be un-mapped directly. So cover that. An important thing to note about freeing a chunk: if you free a chunk and it is not fast sized or T-cache sized, then what can happen is if there's a free chunk directly adjacent in memory to it, it will be consolidated with that chunk if that chunk is also free. So for example, if I have like a free OX100 size chunk here, it's not fast in size, it's not T-cache size, we'll talk about that later, it's just a very big chunk. And I have a chunk directly under or over it, it will be consolidated with this chunk to form a bigger chunk, which if future allocations meet a certain requirement, we can actually remainder this chunk, take a small piece from it to service a request. It sounds complicated, I promise it's not, we'll get better visuals soon. An important thing to note about freeing chunks, besides consolidation, and by the way, I forgot to mention the top chunk, which denotes the end of the heap and where the wilderness is, which is future serviceable memory that you use. It can also be consolidated with the top chunk, meaning that your chunk can just return to the heap. We're not careful in how we do our heap feng shui and like figure out where we want stuff to go. An important thing, and something we might or might not be exploiting today, is the FD and the BK. When you free a chunk, the FD and the BK is actually stored in line in the user data section. So the user data starts here. So for example, we're going to be covering a bug class called a useAfterFree, which can be narrowed down to a writeAfterFree or a readAfterFree. We're going to see why that's useful, because obviously if we can tamper with the links in a linked list, we can tell the heap that something's a chunk when it's really not. The fast bins and the T-cache are singly linked non-circular lists, so they're only going to have an FD, and the other quad word will just be null, except for the T-cache, and we'll talk about that later. But the other lists, such as the small bins, the large bins, which is actually a two-dimensional linked list. I'm not going to really cover that today, but it has a jump list in it. And the unsorted bins, which is going to also be a focus for us. These are doubly linked lists, and they're circular. So, for example, for an unsorted bin, we're going to use Heap. We're going to use main arena metadata. That's going to be a dummy chunk, and that's where the head for the unsorted bin is going to be. If we can read this after we read it, we can also read a GLIBC address. And then if we link something else into it. And again, it's going to be important, not like most of the time, but a good majority of the time to have a heap leak to make certain techniques possible. And if you don't know what linked lists are or you haven't taken data structures and algorithms, I apologize. So this is just a little diagram I made. You see up here is the main arena being stored in libc, and that area in the main arena, we'll just say like main arena, it's probably going to be plus 90 or something. It's going to be the fast bin OX20 head, and if we follow that head here, the dummy address is just A. We'll see it actually points us to the first chunk. This is not entirely accurate because the address should actually point to the beginning of the chunk. This is sort of pointing to the chunk's user data. But this is just to illustrate it better. You see in this chunk, this has an FD address, and that points over here to 2A. And then we see the end of the singly linked list is null, which denotes the end of the linked list. We see the prev in use bit is set, and we see the prev size field is set, which at the beginning, since there's no chunk that's previously free, that's just going to be null. So you see the linked list implementation. We see how the FD is actually stored in user data. Now we're going to illustrate this a bit. So again, if you want to follow along, feel free. This is the same binary we're going to be using for our challenge later. The first binary is the source if you want to look at it. Second binary is the binary, or second link's the binary. Third link's the template file, just to make life easy. So let's run this binary with GDB. We see we have a few options. What I'm going to go ahead and do is I'm going to allocate a chunk that is beyond the size of the fast bins. The fast bins only store chunks up to size 0x80, and the Tcache only stores chunks, I think, up to size 0x600. We'll talk more about both of those later. Fast chunks can be Tcache, but right now we're just going to focus on getting a chunk in the unsorted list in here, just to make life easier. And we're going to see how we can overwrite the unsorted lists BKs and FD, and also read it out. So we can basically tamper with heap metadata and then request a chunk size that allocates this fake chunk we've made. Lots of the time in heap exploitation, the first primitive you might want is overlapping chunks, so you can read something useful, or a fake chunk, obviously, so you can have an arbitrary write. I'm going to go ahead and malloc. I'm going to request a chunk size of 500. Or 600, let's do that so it's not Tcache. A good way to request a chunk of a specific size is to just subtract 8 bytes. So we're going to allocate that. And remember when I talked about consolidation, we're going to want to allocate another chunk of any size. We'll just do 0x18 here. That way it's not consolidated with the top and returned to the heap when we free it. So if I press Control-C to break, if I type in viz, which is a pwn debug command to view the heap, it's kind of a big chunk we allocated. This right here is the Tcache. We're going to ignore this for now. But this is our chunk. We see it's 600 bytes. Prev in use is set, followed by our next chunk, which is our top guard. It's 0x30 bytes because I forgot to type in 0x18. So I typed 0x20 by accident, and it was aligned to 0x30, but the top chunk size doesn't matter. We're just using this so that it's not adjacent to the top chunk and it doesn't get returned. We can view more of the metadata with the heap command. This is the chunk we allocated right here for 600 prev in use, and then our top chunk size. We're going to continue, and we'll try editing it. So I edit it. Oops. Not supposed to do that. I edit it, I read it, we see that arrays are in here. What I'm going to do now is free this first chunk. And if I read it, we see we have a bunch of weird gibberish bytes that are not UTF-8 printable. If I go back to the heap right here, we can see that this is now linked into the unsorted bins. We have our unsorted bins FD and BK. A thing to note about the unsorted bins is it actually has a dummy head on the main arena. If I use pwn debug's unsorted bin command, we can see that this is actually on the main arena plus 96. This is the unsorted bin head. That's where it starts. We can look at the main arena a bit more. Arena. I'm not really good at spelling. I think it's 0. Yeah, okay. So if we look over here, oops, we see that in the main arenas, at this address in the main arena, we're going to add 8 so that we're at E0. We see it points to our heap address, which is where our chunk is stored, and this is linked back into the dummy chunk on the main arena over here. So this is the FD and BK. Zoom out a little. We're going to continue. So we got a leak. This right now is a libc leak because it's leaking the main arena. Just to denote, if you're on a multi-threaded program, every thread has its own arena. So if it's not the main arena, it's not going to be a libc leak because only the main arena is in libc. So we got a libc leak. If we wanted a heap leak, we could just add or free another chunk into the unsorted bin, and that would be stored on the heap instead of back to the dummy chunk. But what we're going to do now, we're going to edit. We're going to choose this. What I demonstrated before was a read after free, which allowed us to get our leak that we might use. We're going to do a write after free now. Choose this already free chunk. We're just going to put a bunch of A's, right? If I go back here, we can see that the FD and BK is overwritten with A's. This actually broke Pwn debug a little bit because now it doesn't think this is linked into the free bins. But it still is. I don't know if this command will work. Yeah, it probably won't. But if we go back to the main arena, we can confirm that this is still in the free bins, or the unsorted bin. And we see, yeah, it's still linked in here. So if we continue, let's request a chunk of the same size. We see we get a segmentation fault. This is probably because of the unlinking check that the unsorted bins does. Recall that to unlink something from a bin, you have to copy over the FD and BK. And GLIBC actually checks to make sure those are valid addresses, which obviously 414141 is not. So yeah, we can see how a use after free vulnerability can be used to potentially trick malloc into allocating a chunk that is not actually a heap chunk. So let's go over the bins in a little more detail before we start doing anything too cool. The fast bins, as I mentioned, are singly linked free list. They store chunks of sizes OX20 to OXB0. So I was pretty off. It is a singly linked list, so the first quad word of user data is utilized as an FD. Again, it doesn't have a BK, that's just going to be nulls. Malloc actually has a fast size integrity check when allocating from these bins, meaning we have to do a bit more when we're linking fake chunks into a fast bin list, because Malloc is actually going to follow the FD and make sure that there's a size field at the right spot, which is honestly not that hard to overcome. For example, because of ASLR. ASLR entropy is largely unguessable, but I'm sure if anyone here's touched the binary, we can recall that it usually starts at OX7F something. That's a size field of an OX80 bin with all the flags set. So we could just offset an address like that and trick malloc into a fast size bin, or fast size chunk. And chunks that are fast size will be put into the corresponding fast bin. This depends on if the T-cache is enabled or not, which it honestly likely will be on anything past like glibc 2. I want to say like 2.3, I think. That sounds right. We'll go over the T-cache shortly. But for now, any chunk under OXB0 is going into the fast bins. Fast bins only has an FD, so it's a nice, easy data structure, singly linked list. We see in my screenshot here how it's working. The unsorted bin, this is probably the most complicated bin we'll be talking about, and probably the most complicated bin, actually. The unsorted bin is a non-fast size bin that stores chunks of any size that are beyond T-cache or fast size range. It's a doubly linked circular list, so there's a tail that points back to the head. And basically what happens is when we have a chunk, we free it, and it's not serviceable to be put in the fast bins. It will be put in the unsorted bins, where next time we call malloc, it actually gets sorted into a small bin or large bin, depending on the size. So free actually doesn't handle the unsorted bins. It only puts stuff and links stuff into them. So if we call malloc, anytime the unsorted bin is populated, it will be searched for a chunk that is serviceable. This is going to be a bit much, but just stay with me. It will make sense, I promise. During iteration, we'll do something called a bin map search. It's basically going to scan all chunks it comes across into the small bins or large bins until it finds an allocation that meets the request that we called malloc for. So it finds a chunk, it doesn't match the service request size we wanted, so it searches that or it sorts it into the smallest or the free list, or the smallest or the large list, and then it goes on until we find this chunk. So any chunk past the chunk we service is not going to be sorted for this iteration, right? Its two first quad words of user data contain an FD and BK respectively. We saw that. A dummy chunk is also linked into the main arena, which we also saw. And since chunks are consistently unlinked from the unsorted bin metadata can be targeted in unlinking attacks, which are pretty cool, and we will talk about them briefly. Just to quickly mention it, if you've ever taken DSA again, recall to remove an element from a linked list. Here, for the unsorted bin attack, we're removing an element from the end of the linked list. We actually have to copy the linked list, or we have to copy the linked list BK over the previous element or over the head, so that it gets nulled out of the linked list. We want to get rid of that element and delete all references to it. But we can actually use the fact that it follows the BK to copy the value over, and we can overwrite that BK and point it to any value. And it's basically just going to write a GLIBC address over it, which can be useful because there are certain there's a lot of things that are useful that can be done with overwriting a very large value. You can overwrite it in some sort of metadata that's important. There's the global max fast variable on the main arena, which has been used in the past for heap exploitation techniques by basically setting it really high and making any bin or any size chunk serviceable to the fast bins. We'll go over that more later. And worst comes to worst, we have unsorted bins. You request a size of X, and the unsorted bins does not contain a size serviceable for X. What it's going to do, it's going to do something called remaindering. We're basically going to take the last chunk, which is also the last largest chunk. We're going to cut a piece out of it, the exact size needed to service the request, and then the remainder will be linked back into the small bin or the large bin. Visual here on the right. The T-cache. Okay, so the T-cache was introduced in 2.26, and the T-cache should be, honestly, the first thing we should learn about because it makes exploitation very easy and circumstances where it can be exploited. So why the T-cache? We talked earlier that GLIBC's malloc is derived from PT malloc, which is for multi-threaded programs, right? So the T-cache introduces this easy multi-threading concept and safe multi-threading concept. It used to be multiple threads which share an arena, and we know multi-threaded programming is hard, right? You can't have multiple threads accessing the same arena where they all have different data requirements as to why they're using the arena or the heap. They all also got their own heap. So the T-cache was introduced so we wouldn't have to keep locking and unlocking the arena, make stuff a little faster, right? So what the T-cache actually looks like, you can think of this giant chunk, which is on the heap. You saw it briefly in the earlier demo. It's going to be the first chunk, and this is sort of the T-cache arena. The T-cache is a struct, and its attributes are counts and entries. So the T-cache is going to service sizes, I believe, I can't recall, I'm pretty sure it's up to OX600, I want to say, or OX500. And basically, once we service something and it gets put into the T-cache after we free it, its relevant counts entry is going to be incremented by 1. So we see here I have, like, in this example, it's kind of hard to see, but I have 5 OX20 fast bins. And the entries, the specific entries field is going to be populated with the head of that list. So that entries field is populated with the head of T-cache OX20. Now, the great thing about the T-cache is it's stored on the heap. So if we can do something weird, like write to other places in the heap, cause some weird stuff to happen, point something backwards in the heap, which we can by just overwriting, like a byte, for example, can actually overwrite the T-cache arena and obviously store a fake list in there. We can decrease the count or increase the count so stuff gets allocated into the fast bins instead. Lots of cool stuff we can do. We talked about why the T-cache. We talked what does the T-cache, how does the T-cache work. Security risks. For us to link a fake chunk into the unsorted bins, we have to pass the safe unlinking. So we actually have to make sure our FD and BK are somewhere writable if we're going to unlink it from unsorted bins, which is not easy to do all the time. And not only that, those wherever that FDBK points to has to be writable, but it also needs to contain it's expecting a next or a pre-field to be there, so it actually has to point back to the chunk that we're pointing at, which obviously wouldn't make sense for us to be able to have that much control. Otherwise, we wouldn't primitive in the first place. The fast bin has the size check, right? So we need to make sure it's fast size, and we'll follow the FD and say, hey, is there a fast or is there a size field here? There are lots of GLIBC exploit mitigations we'll talk about. Most have been bypassed a lot by much smarter people than me. The T-cache is kind of the exception because it really doesn't have any exploit mitigations. We can just straight up link a fake chunk into here and be on our way. Doesn't check for anything. The only thing it does check for is duping. I didn't talk about duping previously, but duping started with the fast bins. You might know it is a double free. Basically, if we have a chunk that is already free and we free it again, it's now linked into a free list twice, which is bad because we can actually allocate a chunk and it will still be in the free list. So we can overwrite the FD and DK that way. There's a fast bin check, which checks basically when you request to free a pointer, free or int free is going to check that this pointer is not at the head of the fast bin list. And the reason it does this, when it comes to the heap, it's whatever's faster over what's more secure. So obviously iterating over a linked list is going to have DSA people can correct me, but I think like O event time complexity. However, the T-cache actually has the perfect mitigation to this by not just checking the head, but iterating through the whole list. And the reason it's allowed to do that without impacting speed is because free or T-cache entries can actually only have a max bin size of 7 for GLIBC for every bin that's in here. So, for example, if I free 7 OX20 entries into the T-cache, it's going to start freeing into the fast bins again. This value is what 7 is what you're going to see on GLIBC. It can be modified with libc tunables and other things to be different values. It might be different values on different distros, but let's just pretend it's 7 all the time right now. And yeah, in a lot of scenarios, the presence of the T-cache can actually make exploitation much easier, which we're going to see soon. So we'll go over some techniques. If any of you have ever looked into heap exploitation on your own, I'm sure you've come across a House of Blank. The first heap exploitation techniques were released in something called the Malik Maleficarum. You can find it on Frack if you really want to read it. It's an extremely nerdy email. And the guy basically discovered, I think it's 3 heap exploitation techniques. House of Crime, House of Spirit. Forgot what the other one is. But basically, a house technique is a way that a person has been able to derive a few primitives that you get, such as maybe a double free or a use after free or a heap overflow or a 1-byte overflow, and utilize either GLIBC metadata, heap metadata, to basically get code execution independent of whatever the actual target program is doing by just abusing how GLIBC and malloc works. So for every libc version, people have been discovering new techniques that utilize corruption on the heap. modify stuff such as metadata, important GLIBC structures. I kind of briefly talked about that when I hinted that we could use the unlinking attack to overwrite global max fast. But these heap exploitation techniques can actually get really cool. There's still a heap exploitation technique discovered by Project Zero that you can do today. And the one primitive you need for an arbitrary write is a single null byte overflow, which actually does still occur a lot because people don't know how to parse strings. So we can do a short exercise here, right? Because of the nature of how ptmalloc stores data, even small off by one vulnerabilities can be leveraged to gain full code execution. Imagine you had a single null overbyte, right? In this chunk you're overflowing from, there's a chunk adjacent under it, and it is in use, it is not free. It has a 3-digit size field. So if I overflow that with a null byte, I can flip that 1 that says prev in use to a 0. I can cause topside or upwards consolidation with a chunk that's already freed, right? I can remainder it. There's lots of stuff you can do. This can give you a libc leak and an arbitrary write if you go far enough. If you want to read more about it, just Google Project Zero overwrite or Project Zero 1 byte overflow, something like that. And if you want to learn more about specific heap techniques, Shellfish's How to Heap, great resource. And this guy's blog is pretty cool. It tells you the heap exploitation techniques, mostly hash techniques, and also tells you if they're still relevant or not. Because some of these techniques are really, really novel and cool, but really stupid at the same time because they no longer work, right? But heap exploitation is still very relevant today, and it was relevant back then. It started with owning the Netscape browser, and today, I don't know if you guys watched Live Overflow, but he's been releasing a series on the WebP parser, publicly available one that everything, I don't remember what it's called. But this bug is actually a heap overflow, and we've just figured out, I don't know if you guys heard of Pegasus, but Pegasus's way of getting initial access to devices on iPhone, Android, Windows, Mac, they all use this one bug because they all use the same WebP parser that had a heap overflow. So it's still a very relevant technique, and it is very much out there in the wild, and it can be pretty dangerous. What just happened? All right. Talk about some cool glibc mitigations. Many of these techniques have been partly or fully mitigated with checks and asserts implemented in different glibc versions. If you ever encounter a mitigation, the best way to learn what it's doing is to just read the source in code browser, or obviously Google it if it's well documented. So right here you can just see an example. I tried to free a certain chunk that I had corrupted, and I got hit with a mitigation from int_malloc. I switched the frame to 5 on the back trace so I could be in the libc message function and view the stack, and it said, unaligned Tcache chunk detected, go on code browser, see what that's doing. And I mean, in this case, the message kind of says what it's doing, so I really wouldn't have to look, but we can see here, it's doing a check aligned okay. To click that, see what it does. There are also other allocation functions such as realloc, which resizes chunks, and how it actually does this is free chunks and then allocates a bigger one for both of them. Pollock, which you'll see in the wild if someone knows what they're doing, it actually zeroes out return chunks. So if I want to do a read after free, it wouldn't work because once I allocate my chunk, it's going to overwrite all the null. They can behave slightly different, but I'll implement int_malloc, which is the core fundamental malloc functionality that we're seeing. And also, not all mitigations are foolproof. Okay. I think we still have plenty of time, so I'll give you guys a moment to try this. If we get stuck or if we say, you know, like, screw it, I don't want to do it, we'll just go over it together, see how we can do this. We're doing this on a binary, most recent version of GLIBC, and most exploit mitigations are related to the stack are on. The only exploit mitigation that isn't fully on is RelRo, and we're going to see why. But I could have also enabled full RelRo, and it would have still been exploitable to the point of getting a shell. I just wanted to disable RelRo so that it would be easier. There are two ways to solve this, possibly more. Hopefully you can do it. If you get stuck, try researching a mitigation I didn't talk about, but could talk about since we still have time, called the safe linking mitigation, which was introduced in GLIBC 2.32. And for context, I don't really talk about RelRo either. There is a section in a binary called the global offset table. And if you have Pwn debug or Jeff, you can figure out where that is by just typing GOT as a command. And for all the C sharpies or whatever, a global offset table is kind of like a Heap table. It basically stores the real-time addresses of dynamically loaded functions. So for example, read, printf, fgets. Basically, when you call that, the program's going to go to a global offset table and follow whatever's stored there. So if you overwrite a global offset table value, next time printf is called, it will call whatever you overwrite it with. Pretty cool. So that's some context. Would we like to try it, or y'all just want to see if we can walk through the solution together? I'll walk through it. Alrighty. Make sure what slides are left. Oh yeah, nothing. I might just do this slide first before I do the walkthrough. That way I can give everyone a chance to get questions out if they don't want to do it. But some resources we can use. Shellfish How to Heap, Azeria Labs. It's mostly focusing on ARM, but it's pretty much the same as AMD 64. Nightmare, Max Camphor's introduction to GLIBC heap exploitation, which goes over a very early technique, but it's a good way to learn heap exploitation. Heap Lab if you're not a brokey, and there's lots of heap challenges on TCTF, which is our CTF site, under Cathex's corner. There are a lot of heap challenges. Yeah. Anyone have any questions before I move on about the heap or the heap exploitation or anything specific? Alrighty, cool. Alright, I'll get out of here. Again, the demo binary I provided is fully exploitable. And I also gave you guys this template binary right here. This basically is a pwnable script. You can see I already set everything up with you. I linked your system's libc so we can interact with it using pwn tools, start a process, and I made specific functions so that we can interact with the binary without having to like send the line after we get these two arrows and do all that over and over and over. So you can see in this template, I provided example usage. So chunk A, we'll just call malloc OX18 for an OX20 size chunk. Edit takes whatever malloc returns. My Python script's just going to return an index. So edit chunk A, make it this value. So this is going to overwrite chunk A's FD. And then free chunk A. So free takes an index, edit takes an index, read takes an index, malloc obviously takes a size. I didn't mention this before, and I'll briefly mention it now. I forgot to start GDB. We see here that this Tcache chunk, it has our FD, which if you can, read that and hopefully see that, let me help. That's actually not a pointer or anything. We're going to talk about that. This is not the value it should be. We're going to talk about that. It's the same point. But normally, the second quad word of user data in a Tcache-free chunk is going to point back to the Tcache chunk. We can just think of it as Tcache arena. That's not technically correct, but it's a giant blob of memory that stores metadata, so at the same time, that's what it is. So this should actually point back to here. And another pretty important thing I forgot to mention about the Tcache is members of the list. Unlike any other bin, the pointers don't actually point to the beginning of the chunk. They point to the beginning of the user data, which is kind of odd, but it's not going to make too much of a difference for us. So I mentioned before that the Tcache is a singly linked list where the FD points to the next chunk. So why is the FD here pointing to obviously not a valid memory address, right? If I view the Tcache bins using pwn debug commands, it says that it's pointing here. We see that that's just not the case. This was introduced in GLIBC, I think it's 0.32 or 2.32, called safe linking. And basically, it complicates our exploitation a little bit by requiring additionally to our overwrite, we need the additional primitive of a heap leak. Because what this actually does is it does a bunch of bitwise operations with our pointer. And it does that just using a heap address. I think you can Google it and correct me. We're going to look at the script and see what it actually does. But if I recall, all the mitigation does is it takes the heap address of our FD, bit shift right to 12, and then it XORs it with that value. So it will XOR our point with whatever this is, bit shift right 12. That's all it does. So obviously, XOR, we all know that, you know, it's the inverse property. We can get any one value if we have two. So all we would really need is a heap leak, and then we can do all that mumbo jumbo ourselves. So if I look over here at the solve, and yeah, I use nano, I'll make you happy, Jax. We can see what we're doing down here. Or where is it? Okay, so the first thing I'm doing, and I'll just illustrate this to make it much easier. The first part of this script is I'm getting my libc leak, because I'm going to need a libc leak because I'm going to need the address of system, because I want to call bin bash eventually, or bin sh eventually. So I'm getting that libc leak first, and I'm also being a bit of an OCD guy by consolidating it all with the wilderness afterwards. So we see what I'm doing by leak. I'm requesting an unsorted bin size, a top chunk guard, same size. The heap link, I'm just requesting another chunk because I'm going to free this chunk into the unsorted bin. That way the unsorted bin points to a heap address and not back at the main. And another top guard. And I'm going to free the heap link and free the leak. And we're going to see what that's going to do in a second. I should actually put this, after I do all these printouts so that we know we leaked something. Make sure GDB is attached as well. I also added the GDB option to your guys' template so you don't really have to do too much. I'm just going to close binge. I don't know why it's open. Continue. Viz. And, oh yeah, that's actually, okay, so right here, we see we're pointing to the next chunk, so that's 290. Unless I return this to the heap, which I think I did because this has a prev and size field. But the point is I linked another chunk into the unsorted bins. That way I would have a heap leak as well as a libc leak, because this points back to the main arena. If we view the unsorted bins, we see that we added a chunk in here so that we get a heap leak. If I go back over here, we see we got our libc address and we got our heap address. We just subtract the constant offset to get the base address for both. Going beyond this, oops. We go a bit farther down. We see that our next goal, since we now have a heap leak, is to corrupt a free chunks FD so that it points backwards towards the start of the heap. That way we can start writing into the Tcache and have our overlapping Tcache chunk. So we can basically modify Tcache metadata, modify the Tcache counts field for a specific size, and modify the Tcache entries so that it points to an arbitrary address, which we're going to put on the GOT, and hopefully overwrite something cool with system. At this point, I said earlier there are two ways to solve this. At this point, we've gone one way. So if you want to figure out the other way, I'd advise you look at the read function and what it's doing. We're exploiting the GOT here. It's also possible to turn this heap bug into a stack bug by allocating a chunk on the stack. Won't go over any more than that, so you're welcome to try. But yeah, we see we're going to request our two chunks, chunk A, and then our poison chunk, which is going to be the chunk that will overlap with the Tcache. Where in here am I? Free chunk A, free poison, so that way they are now linked in a free list. And now we're going to use our write after free to edit the free poison chunk and overwrite its Tcache FD to point back into the Tcache, and then request a chunk until we get that Tcache chunk, and then we can write the Tcache. You see here, all this weird bitwise arithmetic I'm just using to pass the safe link with the heap leak. So I wanted to point to the start of the Tcache, doing the bit shift 12 XORed with the heap address. And then we're poisoning it. This value, once we do all this, is going to be the weird scrambled value we saw before, but if we decode it, it's just the address we want to be next in the linked list. So let's try it. Oh, geez. Try and decide how far I should go in these steps. We'll just go up to here. Do solve GDB. What did I screw up here? Can anyone see what I screwed up? Where? What did I do? From not found. No closing parenthesis. Or, oh, yeah, you're probably right, bro. All right, yeah. Don't do what I just did. Anyway, continue. We'll break. We'll have a look at the state of the heap, which hopefully is not too bad. Well, I breakpointed too early. Heap stuff takes time, so you might want to let it run for a bit before you breakpoint. So I'm going to do continue. Unpack requires a buffer of 8 bytes. I'm just going to run that again because we might have been unlucky with the address randomization. Okay. Okay, we're fine now. Viz. We see that that pwn debug even recognizes that our address is valid because the Tcache denotion still works. And we see that we've modified this value to this value, my bad. It's going to point back to here. I'm not going to decode this because that sounds like a lot of work, but just from the last 2 bytes, we can see that 14 EB it's gonna be around here, right? This is gonna be the Tcache counts field for our relevant size that we chose. In the most recent version of GLIBC, Tcache count sizes are going to be 2 bytes. It was 1 byte before, but now it's 2. I don't know why. But this is our size field for, I think it was, oh yeah, right here, OX4 410. Our entry. Or I guess we haven't gotten to the spot where we're going to malloc the chunk we just poisoned, so let's try that. Oops. What chunk size was that? OX408. OX408. No crash. That's good. I think we need one more. You know what? We're just going to see if this works by pressing continue. Actually, I'm not sure what index that was, so I'm just going to brute force it real quick. There we go. We're going to put a bunch of A's. Hopefully, we screwed with the Tcache. No, we didn't. We are still in allocation short. So I'm just going to run the solver up into the point where we request that poison chunk. Where is that in here? Over here. So here we're going to request the overlap chunk. This is going to overlap the Tcache. And then this edit is kind of a long payload. What I'm doing, doing 63 times, so I'm just filling up the entry fields that don't matter to me, which you actually really don't have to do unless you're going to request that Tcache size. Usually, corrupting heap metadata won't actually cause the program to crash until you follow a code path that leads it to crash. But I'm still just doing it to keep it clean. This is going to update our relevant count entry. And then afterwards, that address is going to overwrite our entry. So that's going to be the head of our Tcache list that we're forcing, which is OX410. This address happens to point to free, to the GOT of free. The reason I'm doing -8 is to pass the Tcache alignment check, as I mentioned earlier. So it has to be aligned on an 8-byte boundary, like all heap chunks are. That's the only thing that check checks for. Recall that Tcache chunks actually return pointers to the user data, not to the metadata of the heap chunk. So we don't have to do any weird byte arithmetic to get our user data aligned with what we want to overwrite. This is purely just to pass the Tcache alignment check. I'm actually aiming for the free entry of the GOT for a specific reason. Recall that free's argument is a pointer. Recall that in binary exploitation, when you're returning to system, you're also passing a pointer to bin sh to system. So the reason I'm overwriting free is because it makes life really easy, because I can just put bin sh on one of my chunks on the heap and then pass it to the heap. That will free it. Be a normal functionality. You see here I'm going to overwrite free GOT with system. And then as I mentioned earlier, this new chunk I'm creating, I'm just putting the string bin sh in here, right? And then plus libc sim system. So this chunk is going to be overwriting, and we'll visualize this in the debugger soon. But this chunk is going to be overlapping the free function on the GOT. And then recall the first 8 bytes we're not overwriting free, so I can just put bin sh there, which is exactly 8 bytes luckily. And then overwrite free with system. And then I'll just free, which is now going to call system, with the index of this chunk, which is bin sh and then the null byte. So that's just going to be system bin sh. Might be too fast, especially for people who are new to binary exploitation. But I'm going to try and help you out by visualizing it right now. I don't know how to delete a line in Vim, so you guys are probably all right on following along if I help you out. We'll do Python 3, solve. We'll just do solve first without the GDB, and then we'll visualize what's happening. So solve, and it gave us a shell. Let's see what's actually going on, though. Continue. I'm going to wait a couple seconds. Hopefully it doesn't crash. It didn't. We see here it's spawning a dash process. So if I go to GOT by printing GOT, the program's not being run. Oops. See if I can time it. Where is free in here? There's so much stuff in here. Free. That's still pointing to system. Or pointing to the actual free. What I'm going to actually do is just delete the part where I trigger the code execution. Okay. Let's inspect what's going on here. We see that the GOT entry for free now points to system. Recall that's why we needed the GLIBC leak from earlier. And if I were to view some of the heap metadata, hopefully this command still works. It actually might not. Yeah, I don't think it does. It's not detecting that this is actually a heap chunk, which it is. Lots of the time when you're doing heap exploitation, you can screw up your GDB extensions because it uses the same metadata you're corrupting to check stuff, but we can always view that manually. And yeah, you see freeze over in with system. You see that our last chunk, which we overwrote it with, is going to be somewhere on the right. Or actually, this string probably translates to bin.sh. Yeah, so there we have it. That's how you can use heap exploitation to get code execution on anything. I encourage you all to find weird open source shit and report after you find something cool, like a WebP parsing thing, and credit it. All right, thank you all.